pleasure to welcome Gilles Gonçalves de Castro from Florianopolis, who is going to talk about sister algebras and Leavitt path algebras for labeled graphs. Please, Gilles, go ahead.
Thank you. I want to thank Guilherme for the invite. So I'm going to talk about these two words, the sister algebra and the purely algebraic versions of algebras for labeled graphs. So before I start the definitions, I just want to give a brief history of these two areas. So starting with the sister algebras, well, I put that Kunz-Krieger in the algebra, in the generalization of these algebras. Basically, Kunz-Krieger algebras are seen from this symbolic dynamics world. And before that, there was the seminal work of Kunz, where they studied this. Nowadays, we call it the Kunz algebras. In his work, he was interested in looking at the simple infinite sister algebras. But then later, together with Krieger, which is from symbolic dynamics, they realized that these algebras are really closely related with shifts of finite type or these topological Markov chains. And so they started studying these algebras associated with these. Well, in their case, they were considering matrices of zeros and ones, and then you can find some partial isometries in a sister algebra satisfying certain relations using that matrix. In their setting, they were looking at already represented operators. So they were at the time there was no general construction of these universal sister algebras. So they need some kind of uniqueness theorems to prove that well, under certain conditions the algebra they are defined is uniquely defined. But in other settings, well, you could have different versions of the same algebra depending on where you're representing these operators. And I think around that time, in the 80s, what I already some kind of work using graphs, but I think we became more mainstream with the work of Gilles Pascal, Rabin, and Reno in '97. So the idea is that if you have a shift of finite type, you can represent it using this matrix of 0 and 1s, but you can also represent the shift to using finite graphs. And so the idea is that that they were starting to consider infinite graphs well, there are some problems that you at the beginning that they were they only considered what they call this raw finite graphs, because otherwise you have some kind of infinite sum, or even in the symbolic dynamics setting that you want these sequences, infinite sequences. If you have something like infinite meter or sync, you would have some kind of problem if you want just looking at the infinite sequence. And then later they realized that actually you need to look at also finite sequence. So, but then basically here we kind of restart this notion of graph sister algebras, and then from there are a lot of work on that. Another kind of generalization of these Kunz-Krieger algebras are the work of Matsumoto, where they was looking at these two-sided subshifts in general. So there was a small mistake, I think, in his earlier work, and then together with Carlsen, they correct this mistake. So there are actually two versions of the Matsumoto algebras. Another generalization of the Kunz-Krieger algebras is the work by Axel and Lack. Already in the paper by Kunz-Krieger, they are already considering infinite matrices. But as I said, at the time, it was just represented in a certain bounded operation on a certain Hilbert space. And then I think it was '86 that Blackadar worked the universal sister algebras, and then he showed that you can have kind of a universal version of this Kunz-Krieger algebra, at least for finite matrices. And then Axel Lack were trying to kind of find a universal version for the infinite matrices. And at the time, they decided you could not use infinite sum relations But this is actually, we can actually do that. So this is just a footnote that together with Bravo, we've shown that we can actually present these XLOC algebras using intimacy relations. It is already hinted in the work of Blackadar in the 86 that actually any kind of relation using operators on a Hilbert space, you can kind of do a universal version of that. But he only developed for this polynomial relation. So that's why in the XLOC work, they really work hard to find some kind of polynomial relation, but it's a little bit more complicated than just generalizing directly, just taking defining summing and using infinite sums. And so these two classes of algebra, the graph system algebra and XLOC algebra, they both, in a sense, want to generalize Kuhn-Krug algebra for the infinite setting. So one is for infinite graphs, the other for infinite matrices. And they, as far as isomorphisms go, they are not the same class of algebras. So don't fall motivated by this. He defined a more general class of algebras, which is this ultrograph system algebras, which includes both the graph and XLOC algebras. And up to Morita equivalence, actually, they prove that they are all the same. So ultrograph, XLOC, and the graph system algebra, up to Morita equivalence, they are all the same. But as far as isomorphisms go, graph and XLOC, there are a lot of things in common, but they are not. There are examples from one and not the other. And the ultrograph includes all the others too, but it's a little more general. And then in 2007, recent past defined this system algebra for label graphs, and then this actually includes all the previous algebras as an example. So in a sense, they were putting together this ultrograph system algebra and the Matsumoto algebras in just one setting. And there are a little bit more generalizations for in the shift case, and there are this Matsumoto, he considered two-sided subshift, then Carlsen considered one-sided subshift, so it has a different definition of an algebra. Well, after his paper actually, together with Basic and Pascal, they showed that these algebras can also be modeled using labeled graphs. And then you realize when you study this algebra that it's really important that these Boolean algebras and homomorphism between Boolean algebras, and the more motivated by that, Carlsen, Ortega, and Pardo consider this Boolean dynamic consistent, which is not a direct generalization of labeled graphs. Again, you have this a big intersection between the two of them, but they're not exactly the same. And then recently, Carlsen and Kang, they defined this generalized Boolean dynamic consistent, then which includes all the previous one. And then there are two other very important generalization of graphs algebra, algebras, which are the higher rank graphs and the separated graphs. But these two, it's not included in this, so it's still a different setting. So this is for the sister algebra. So you can see from Kuhn's algebra, there are a lot of work that motivate and generalize a little bit more the work in Kuhn and Krieger. And then on the pre-algebraic setting, you have you can go a little bit actually before the works of Kuhn, the works of Leavitt. So in a sense, Kuhn's algebras, the pre-algebraic version already appeared before the works of Kuhn, so in the works of Leavitt. And he was interested in these rings which does not satisfy this IBN property. So IBN stands for an invariant basis number, which is basically if the ring satisfies the property, all modules have a well-defined dimension because all bases are going to have the same number of elements. But if it does not satisfy, then you say that it does not satisfy. You don't have this IBN property. And Leavitt was interested in this kind of rings. So he studied the structure of these rings. And then in the early 2000s, in this work by Ara, Gonzalez, Barros, Buder, and Pardo, they were studying another kind of rings. And one of the examples they were given in their paper, this algebraic analog of these Kuhn-Krug algebras, because now that we kind of have this universal algebra, sister algebra, universal algebra given by generates and relations, you can consider the pre-algebraic version, and then they realized that if you take the matrix which gives the Kunz algebra, then you recover a subclass of the Leavitt algebras. And motivated by this, Argentino, they consider a little bit more general setting. So since the graph star algebra generalized Inscribed algebras, they consider these left path algebras for graphs. There has been a lot of study in deciding for left path algebras, and for the other class that have some generalizations. These appear in an example in a paper by Clark and part of these algebras for Boolean dynamical systems, which is not very well explored. It's just an example of some results on simplicity. And then for autographs, there is a recent paper by Umafa, Baba, and Larky for the left path for autographs. And as far as we know, there was no work only looking at these left path algebras for labeled graphs. And we've started the study of these algebras in published preprints this year. So to get the definition, first we need the definition of a graph. So this is very standard. So we have this quadruple of a set of vertices, a set of edges, and then have a source and range map. In our setting, all graphs are directed graphs. And then for the labeling, we aren't going to label the edge. So we have the set A, which is a set of ladders, and we have this map from the edges to the ladder. So we just put in a ladder on each of the edge. And we assume this map is only because the ladders which are not labeled for any edge you can kind of ignore. And so this pair is a labeled graph. And then when you have a graph, you have this notion of paths on the graph, either series of finite to infinite edges, where the range of one edge is the source of the next. So you can kind of think this: we are walking on the graph. There's another convention that it's the other way around. So the source is the range from the y. If you consider that in the functorial setting, you kind of use the different convention, but then we're going to use this convention here. And we can easily extend this map, the labeling for, instead of labeling only edges, you can label any path, just concatenating the ladders for each of the labels of the edges. And I'm going to call these images of these labels of paths, labeled paths. And since we're not actually labeling the edges, the vertices, we're also going to include this empty word to our labeled paths. So we consider empty word as, and here I'm going to use the omega to identify the empty word. And
so
as for
so the empty word has no label.
Yeah, there's no labels there. So or you can think that the label for all vertices is the empty word in a sense. And then we can consider the set of all labeled paths, the finite labeled paths, the infinite labeled paths, and then sometimes you want just to consider the ones which are length greater or equal than 1, or you can consider all labeled paths. Okay, so for the definition of the algebras, we need not only a labeled graph, but so we need at least this more general thing called labeled space. And to explain the definition of labeled space, we need this notion of the relative range of a labeled path with respect to a set of vertices. So we take any set of vertices and take just any labeled path. Basically, what we do is that we consider all paths that starts in A, so the source of lambda is A. So we take all paths that starts in A, whose label is out. So, and then you look at the end. So you look at the range of these paths. So this is it's called the relative range. In the case for the empty word, since we are basically not walking anywhere, so we just put this as the itself. And we can define the range of an alpha as starting anywhere on the graph. So starting anywhere on the graph, you look all the paths that has this label alpha, and you look at the range of this label. So this form of set is called the range of alpha. And so a labeled space, which is the ingredient that you're going to use to define the sister algebra in the Leavitt graph algebra, is going to be a triple where you have this labeled graph and you have this family B. So this is motivated by the work of Tom Ford, that he used this family of vertices to define the orthograph sister algebras. At the beginning, they just assumed that this family is closed and then find its unions and find intersections. But if you look at the sister algebra, the relative complement is inside the sister algebra. So we can assume already at the beginning that B is also closed and the relative complements. It makes a little bit things more easier, because then we're going to get a Boolean algebra of sets, which is not necessarily unitary. So we do not assume that T0 is B. So there's recently this duality between Boolean algebras and logical space, or Boolean inverse and all that stuff. We do not assume that the Boolean algebra is unitary. Basically, what we lose is just compactness. So instead of looking at only compact space, we look at locally compact spaces. So these non-unitary Boolean algebras. And what we assume for this family is that it contains all the ranges for every labeled path. And it's also closed in the relative range. So it also contains every relative range for every element in the family. And you have this second condition. So the normal is being a Boolean algebra, and this second condition is called weak-level resolving. We can easily show that this relative range preserves union, but we can give examples where this intersection is not preserved. And so we're going to assume that this relative range also preserving intersections in our family. And as I said, the union is it's easy to show that it satisfies. And once you have the union intersection, you can also show that it preserves the relative complements. So these really are Boolean algebra homomorphisms, which we're going to play a role later in the talk. And when we define as I said in the beginning, that there are some restriction on the infinite graphs at the beginning when they define the algebras, but then they define a more general version for any graph. And the idea is that we need this notion of a single and regular vertices, and we have the analog here for these labeled spaces. So the idea is that for each element in this Boolean algebra, we're going to look at all the ladders that can leave this A. So basically, when you have the relative range being different from the empty set, so there's an edge starting in the set A, which has this label, the ladder A. And we say that the set is regular, then it's not only the set itself, but all subsets which are in the family satisfy this property that the set's finite and non is greater than zero. So the set is finite and non-empty. So finite means that it's not an infinite meter, and being different from zero means that it's not only consistent only of things. The set A and set B, they can have sinks as long as you can't isolate the sinks inside the Boolean output. But it's kind of the analog for graphs. And so you get the definition of the sister algebra of the labeled space. So we have this triple, so we have the labeled space. So the original definition by Leavitt and Pasqua is in this paper in 2007, but there are a small mistake there, which they corrected in 2009, but it was not for the general setting. It still have some problems. And the final definition that I'm going to present here is in a paper by Leavitt, Castro, and Pasqua. We actually found this independently. We are looking at the group-wide description of these algebras, and we found that the original definitions are not suitable enough for what we intended. But then later, when we were on the preprint stage, that I think that was Carson that contacted me and said, "Oh no, but we already have this correct definition." So basically, what we have is these projections. So in the graph sister algebra case, the projection associated for each vertex. Now we have this family of vertices, so we're going to have a projection for each set of this family. And in the graph sister algebra, we have the partial isometry associated with each edge. And now we're going to have a partial isometry associated with each ladder of the alphabet of the labels. And the first condition is that these projections satisfy this. It's a kind of a lattice representation of this family P. So it preserves intersection, preserves joins. Sorry. And the M set, you want to send it to 0. And then you have a commuting relation between the projection and the partial isometry. So whenever you have a projection on the left and put in the right, you gain the relative range with respect to the ladder. And then these two conditions is, again, analog to the graph system algebra case. So the projection, the initial projection of the spatial isometry is the projection on the range, and they are mutually orthogonal. So the final projections are orthogonal if you have different ladders. And then this fourth condition is sometimes called the Inscribed relation, which is a generalization of what we have there. The difference here is in the graph system algebra case, there is no, this projection does not appear. It's just projection of their diversities is a sum of the SA star, but in this label space case, we need this projection in the middle as well. I'm going to give you an example in a minute, but we can consider the algebraic version. As I said, as far as we know, we haven't seen this done before, but basically what we do, we take any unit of commutative ring, well, we could consider the star algebra, but we took the approach of using these, what sometimes they call the ghost edges. So we need not only the SA, but we need the stars of the SA to define the relations. The projection, we don't need the star for the projection because since we're not dealing with star algebra, so we don't. It's just if they are just the points, they are not going to be projections in the star algebra setting. And then they have the same relations, but we have to add something else to take into account this star that we don't have for the definition of the algebra. So the partial isometry put it as a different relation, and you have to add this other commuting relation, not only for the SA, but for the SA star. But then we just, instead of going from left to right, you go from the right to the left. And then the last relation is the same as we had before. One thing that is interesting between these two algebras and which happens for the graph case as well is that it has a lot of things in common, and we're going to explain a little bit more later, but basically is that we have a group pod model for both of these algebras. But before we go there, I want to show just a few examples. So the first one is the case for graphs. So we want this to generalize graph system algebras and graph left path algebras for graphs. So the idea is that when you have a graph, you can consider the labels to be the edges themselves, and then the labeling just the identity function on the edges. And you have this family B, and since we are dealing with projection of vertices, when you can sum these projections because they are mutually orthogonal, it's basically they're going to work as a projection of the union of these vertices. So you just take this family B as the family of all finite sets. And then when we take the sister algebra of labeled space, you get the sister algebra of the graph. And when you consider this left labeled path algebra of the labeled space, we recover the left path algebra of the graph. And we can have some kind of converse. There are some sufficient conditions where we can have if you start with the labeled space and then we get the algebra of the graph. So we have these two conditions. So this first one is left resolving. So this means that whenever you have two edges arriving at the same vertex, they need to have different labels. So saying that this restriction is injective. And this other condition, the labeled graphs label finite if there's only an amount finite of edges which have the same label A. So for each A, there's only a finite amount of edges which can have that label. So this left resolve is a very important condition when we study symbolic dynamics. So subject shifts are presented by this label left resolve labeled graphs. And this label finite, well, if the graph is finite, then it's okay. But basically, the idea here for this, when you have these two conditions, so the sister order of the labeled space is exactly isomorphic to the sister order of the graph. When you consider the same family as before, the family of all finite sets of the vertices. So the idea is that when you have this left resolving, if you have a label and you have the vertex where it's arrived, you can recover the edge because there's only one edge. Well, each label will arrive at a vertex. And this second condition is just to say that if you sum all the projections of the partial geometry associated with each edge on the graph algebra, and you sum them, this is basically going to be the projection associated with the level. So we need to be finite for this to make sense. So if we have these two conditions, so we have the kind of a converse for this first result. But not all labeled left, or not all sister algebra labeled graphs are graph algebras. Actually, it's something much more general. And one way of constructing is examples. And then, since this is going to be play a role later on the talk, I'm going to give a little more details here. Is that whenever you have a Boolean algebra, you have this notion of the Stoney dual. So you can always build a topological space, and the way of doing this is consider these ultra filters in the Boolean algebra, and then you can consider as a set the set of the ultra filters, and you can give a base of compact open sets with of this form. So you take each element of the Boolean algebra, you take the ultra filters that contain that element, and it's going to form a base of compact open sets for a topology on X. And if this topology actually, these are all the compact open sets, and you have an isomorphism between Boolean algebras, and you have the other construction. Well, if you start by Hausdorff space with a base of compact open sets, and then this is going to give a Boolean algebra, and you take the dual, then it's going to give a space that's homomorphic to the original one. So this is called the Stoney duality. And so we can kind of make an extreme example in the sense that we are not going to consider any edge at all. So there's no edge, there's no labels. And the vertices is going to be the set of all ultra fields. So we start with this Stoney dual, and we take the edges to be this X itself. And because we have the information of the Boolean algebra, we can actually recover in the sister algebra setting the continuous function vanishing at infinity for X. And in the case of the left labeled graph algebra, we recover this continuous function of compact support. In this case, R is considered to have the discrete topology. So this is the same thing as saying these locally constant functions on X. And since you have these things in all generality, this is going to give a set of examples where we don't have left graph algebra for graphs. I'm going to talk a little bit in a second. But there's we kind of have a converse for these isomorphism in the setting, in the sense that if you start from an algebra, which is here we're going to suppose that the R is an integral domain, but we have an algebra that is generated by both in this commutative in torsion free, you can actually recover this topological space X, and then the algebra is going to be exactly this locally constant function on X. So this result is basically some kind of Gelfand representation for commutative sister algebras, and then using these, we can build a lot of examples
sorry, the algebra is an algebra over R, right?
A is an algebra over R, yes.
Okay.
Yeah, didn't put here, but it's a commutative R algebra. So, for instance, if you take this one-point compactification of the natural numbers, and you take this Boolean algebra compact open sets on here, we can build these commutative algebra of these locally constant functions, and because of this duality, we can build this as a left labeled path algebra. And this cannot be a left path algebra for any graph, because commutative algebras, left path algebras which are commutative, either for graphs or orthographs, they necessarily are direct sums of either the ring itself or the Lohan polynomial ring. And because of this accumulation point of the at infinity, we can check that this cannot be written as this direct sum, so they cannot be isomorph to any graph or orthograph left path algebra. Okay, so as I said before, the reason why people in sister algebras got interested in these left path algebras is the similarity between the graph sister algebras. And as I said, there are a lot of properties that they share. And one way of proving this is building a groupoid model for these algebras. In the case for label space, it's a little bit tricky to describe. But we developed this groupoid model using inverse same groups. So there's the theory by Axel of tight groupoids from inverse same groups. Then we show that these are isomorphic, and then we can have a description of this tight spectrum that appeared in the theory. But more recently, in a work with Kang, we give a different description. Here, it actually is more general. We did for this generalized Boolean dynamical system, but I'm only going to present for labeled spaces. And the idea is that we can kind of consider a topological graph, almost a topological graph, then things are a little bit easier to explain. So the idea is that first of all, that we can, for each labeled path or each ladder, we can restrict the Boolean algebra to being only the set that which is containing the range of the corresponding labeled path. So basically, this is an ideal of the Boolean algebra. Then it's going to be in a Boolean algebra itself. And we consider the corresponding Stern dual. And this Boolean algebra, they're all going to be unitary except for the empty word, which is the original family B, which is might or might not be unitary. And as I said, the relative range is a Boolean algebra homomorphic. And by standard duality, you have the continuous function on the other way around. But because B might not be unitary and all the other B alphas are unitary, then we might have a problem that the pre-image of our filter might be empty. So we need to add this empty here, the empty set to make things work. But the idea is that the relative range using the standard duality is going to give us a continuous function, which is described in this way. So we take an outer filter in A, and then we look back and look at all the sets in A where the relative range belongs to this outer filter. And if you look at the graph example, basically this F is going to correspond to a vertex, and this A is going to be corresponding to the source of the edge. So A there in the graph example is an edge. So if you know the range of an edge and you know the edge itself, you know the source, so you know the vertex. So basically this F map is going to be our source map. And we have another way of building an ultra filter here, which is because this is an ideal inside B. We can take the upper set of this ideal, or in other words, we take everything that's above an element of the filter, and then again, it's going to give us an ultra filter in the family B. And with these two maps, we're going to build a topological graph, or more exactly a topological correspondence. And the idea is that for each ladder, we have these two maps, and we're going to take the joint union. So the edges for our topological graph is going to be the joint union of this set XA. And to make things work, we're going to, instead of looking only one set of edges, we're going to look at two, but here E0 is containing F0, and F0 has this one-point extension topology. So if X omega is a right compact, we can add in an isolated point, but if it's not compact, it's the one-point compactification. And then we can define this map, this source and branch map using, we look at the ladder where the edge belongs, and then use that maps that I defined before for the corresponding ultra filter. And then this is going to give us a topological correspondence. And again, because this E0 is contained in F0, actually we can build the path space as we usually do. I actually contacted Katsura to see if these things work, and he put a preprint on archive, defined these partial topological graphs where it can model this kind of stuff. And then the idea is similar to what to do for graphs, but the definition of a regular vertex is a little bit more complicated because you have to take into account the topology. But then the definition of the boundary path space that we have is the same as we have for finite graphs, or for graphs which are not topological, for discrete graphs. So we take finite paths which does not end on a regular vertex, and we take all infinite paths. And then there's a way of building a groupoid out of that. For those who are familiar with the graph groupoid, it's the same thing. But then here we need to give a suitable topology for this to work. And there is a nice topology for this, which is, in this case, the groupoid is going to be amenable, Italian, Alderfoot. So it's very well-behaved groupoid in order to consider the algebras. And then, so as I was saying, before we're building this using inverse and group theory, and then we showed that using this topological correspondence, we actually get back to the one we had before. And using this, we can show that the C-star algebra of the label space actually is the C-star algebra of this groupoid. So this was done by Carlson, Ortega, and Pardo in the setting of Boolean dynamic system, but there they need some, as I said, this does not contain all label spaces, and they need some kind of countability properties. Then we've done it for label space, and now more generally, we've done it for this generalized Boolean dynamical system with no hypothesis whatsoever, and generalized Boolean dynamic system works. And for the left path algebra, now we consider the Steinberg algebra, the same groupoid, and then we obtain the left labeled path algebra. And well, then once we have the same groupoid given both the algebra and the C-star algebra, so the left path algebra, C-star algebra, we can get some kind of nice results which are going to be similar to both of them. Like some here we have the gauge invariance theorem, here we have the graded invariance uniqueness theorem. We can have the generalized uniqueness theorem as well. We have this core subalgebra, and here we're going to have the analog here as well. But I want to explain briefly the simplicity of these algebras. So for simplicity, the idea is that in the graph case that in groupoids in general, for the simplicity, since we're dealing with amenable groupoids, what we're looking at is for the groupoid to be effective and minimal, and when we can describe these conditions using only properties on the labeled space. So in graphs, you have this condition now would say that every cycle has an exit. Here it's going to be the same thing, just the definition of cycle is a little bit more complicated. The definition of exit is a little bit more complicated, but the idea is the same, that you have this conditional which every cycle has an exit. And then we can show that this is our equivalent. So having conditional being topological principle being effective, they are the same. Usually, if this is second countable, this is always the two are the same. But usually, effective is not necessarily topological principle, but we can show using the isotropy of the groupoid that is all the same, even if you don't consider the second countable setting. So the conditional gives us the groupoid being effective. And for minimality, you use this notion of these hereditary saturated sets, which already appears for the set of ideals on graph C-star algebras and graph algebras as well. And so since we're looking at simplicity, this also appear here, but now for the minimality. And the idea is that the groupoid is going to be minimal if and only if these the only hereditary saturated subsets of B are the empty and the whole family. So basically, if you have another one, you could find a closed invariant subset of the groupoid, which is related to this hereditary saturated subset. So we kind of have a relationship between these and the invariant closed subsets. So that's why minimality is equivalent to this condition. And so just to illustrate an example of results being the same for the graph, for the sister algebra case in the left, the pre-algebraic setting, we have this characterization of simplicity. So the sister algebra is going to be simple. Now we need R to be a field. I'm gonna remark this why do we need that. So whenever we have this R a field, so the sister algebra is simple if and only if the left label path algebra is simple, and if and only if the this label space satisfies this condition now, and the only hereditary saturated subsets are the empty set or and B itself. Because this is the same as saying that the groupoid is effective and minimal. Since the groupoid is already minimal, we don't need to talk about the reduced sister algebra, just the sister algebra of the groupoid. And actually, in the pre-algebraic setting, we need R to be a field, because if R is not a field, then we can find a non-trivial D of the ring. Then using this non-trivial D of the ring, we can find the non-trivial Ds of the algebra as well, even if the groupoid is minimal and effective. So R is actually being a field is necessary for this algebra to be seen. And just to finish the talk, there's another way of looking at this algebra, another kind of model of this algebra, which is using this partial action. I think I have around around 5-10 minutes. So I'm going to go a little bit quick here. So partial action is just an action of a group. Instead of being isomorph, or in this case, homomorph between the space X, we have this collection of subsets, which are open subsets, and then homomorphs are going to be between these subsets. So for each element of the group, we have these open sets, and then we have these homomorphs for each element of the group. For the identity of the group is going to be the identity of the whole space. And this third condition is that in the action case, this should be equal. The composition of phi of S and phi of T should be F of ST. But in the partial action, this is just equal when it makes sense. So we need this condition on X. And if you look this, and in the sense of the function being graphs, graphs or graph of a function, this is just basically saying that the composition is contained in the phi of ST. And we are going to be only looking at the partial action of the free group. And then when we look at the free group, we are interested in partial action where we actually have this equality whenever the length of the ST is the length of S, but plus the length of T. So when we have this happen, we have the same saturated partial action. And then we also want to look at these orthogonal partial actions, meaning that for every generator, the domains of the phi minus one is going to be disjoint. So just for the generators, you want this to be disjoint, and then you have an orthogonal partial action. And then this is more in general. If you have an action, a partial action of a discrete Haldov a discrete group on a Haldov space, of this base of compact open sets, because we want to work both on the sister algebra and the pre-algebraic setting, we can define a partial action. If you have this partial action, we can define the dual partial action both on the sister algebra of X, or the C0 of X, and the locally constant function of a ring. And you can build, so from the topological partial action, we have this transformation group points. For the sister algebraic partial action, we have the sister algebra cross product. And for the algebraic partial action, we have the algebraic partial cross product. And then there's a result by Abadi, which is much more general, which I'm saying here. It does not need to be discrete. It can be any any topological group, it works as well. The sister algebra of this transformation groupoid is isomorphic to this partial cross product. And then more recently, this I think it was PhDs of Fabiani Goethe, they shown that for the Steinberg algebra as well. So the Steinberg algebra of the transformation groupoid is the partial cross product, the algebraic partial cross product. And then we actually shown that there's a way of building an orthogonal semi-saturated partial action of the free group on that boundary path space of that topological graph that done. Actually, we done for the space that we got from the inverse same group, because they are isomorphic. We can consider this on that space that I explained, and in such a way that the transformation groupoid of this partial action is exactly that boundary path groupoid that I had before. And as a consequence, I can describe both the sister algebra in the left label path algebra for the label space as cross product as well. And just to finish, actually, we have some kind of converse for these results. So we only done it for the algebraic setting, but I'm pretty sure that we can do it for the sister algebra setting as well. We want to describe some partial actions, well, partial cross product as being the left label space of some label space. And the idea is that if you have a installed space, so that means that you have a Hausdorff space for base of compact open sets, and you have this semi-saturated orthogonal partial action of the free group on the set, with the hypothesis that the domains of the homomorphisms are all compact open, except for the identity, because the identity is the whole set X, and X itself does not need to be compact, but all the other domains are compact open. Then we can model this partial action with a labeled space. There is a labeled space and the homomorphism between X and this bound cleft space that we found before, and in such a way that this homomorphism is equivalent with respect to the partial actions. And so we get the transformation groupoids are the same. And I'm working with that we are trying to remove this compactness condition here. We are only consider cloping, and then when we consider cloping, we get this generalized Boolean dynamic consistent. So it is a work in progress. And then in the algebraic setting, if you have this torsion-free commutative algebra generated by idempotents when R is an integral domain, so we have this that R A itself is this locally constant function on a topological space, and then if you have this again semi-saturated and orthogonal now an algebraic partial action, and then this condition of UT being compact open is the same as the ideal being unitary for every element of the free group, which is not the identity. Then we can model, well, since you have the algebraic version, you can have the topological version, and the topological version is modeled using label space. And then because the left label path algebra is the cross product, then in the transformation groupoids are the same. And then we get the result that we can recover this partial cross product as a left label path space. And as I said, I think this probably going to work as well in the sister algebra setting, as long as this A is a sister algebra generated by projections, a commutative sister algebra generated by projections. I think it's going to be the same thing. And in this, if you want to remove this unitary condition here, I think we need to go to this generalized Boolean dynamic consistent. So I think this is a very interesting result that there's this. I think it's a big class of cross products that can be modeled using these left label platforms. And that's what I had to talk about. Thank you.
So thank you very much. I have a number of questions. So the sister algebras of label graphs are nuclear, aren't they?
Yes, they are nuclear. Yes.
Okay, and so yeah, and so do you have a theorem that guarantees not only simplicity but pure infinite simplicity?
There are some characterization of purely infinite, but there are a lot of restrictions on the labeled space. I think this is a bit special. I think they write some results, and then there is some results I think by Jung and some of her collaborators. I'm trying to work with Kangi to see if you can do this in the general setting, but we don't have a full characterization in the general setting. There are some partial results and so some classes of labeled space that you can characterize this purely infinite and simple.
So, but instead, so what I was thinking along the lines that, I mean, if it is, so if every labeled graph sister algebra, which is a Kirchberg algebra, so these algebras, these Kirchberg algebras, every one of them is isomorphic to one of these Katsura algebras.
Yeah.
And so this would be Katsura algebras. Those, I mean, at least there's a family that are Kirchberg algebras. So and well, and in the, I suppose what you know for in this line about purely infinite simplicity for sister algebras, you also know it for the Leavitt side. I mean, the purely algebraic. One or
yeah, actually, since this definition is kind of new, I don't think there is still any result on this, at least for the algebraic setting of being purely infinite. In our paper where we introduced these algebras, we just look at the simplicity and this uniqueness theorem. We didn't look at the purely infinite, but I suppose there might be some characterization which are the same, although it's a little bit more difficult because as far as I know, the groupoid characterization is just a sufficient condition. So I think the groupoid being locally contracting is sufficient to be really infinite, but it's not equivalent. So so it's probably going to be a little bit more difficult to give a full characterization.
And what about the K theory in either the C-star or the algebraic case?
In the C-star algebra case, there is this paper by Basic Carson Parks where they consider the K theory. There they describe it as a finite algebra, and then they use the K theory as a finite algebra to describe it. So they have several examples there. And for the pure algebraic setting, we still didn't look at that yet.
So that's the fact that you can describe it as partial cross product help in that respect? When do you have a general theorem about K theory of partial group products with a free group?
I haven't looked at that. Yeah, I'm not sure.
Okay, so are there any further questions? Sorry to ask myself all the questions. Let me see. Wait a second. Okay, so if there aren't any further questions, I would thank Gilles again.